this part of our lecture, we are going to discuss the formulation of model predictive control problems further. Previously, we have mentioned about the mathematical system representations, and now we are going to dig deeper into the cost function structures and constraints. So let's start with the cost function. So cost function is basically a tool how you are going to punish if the system is not behaving in the direction that you want it to be. And let me give you a very brief example regarding with it. So later on we are going to make some modifications. And this could be as minimized based on the control input from k is equal to 0 to np y minus y k ref, let's say squared, plus sum from k is equal to 0 to nu u minus uk, let's say ref squared. So I think we need to stop here for a while because there are some new concepts here, new terms here. We have our output variable, we have our reference for this output, and on that side of the cost function we have the input and the reference value for our input. So it shouldn't necessarily all the time like that, but this is just an example. And we have some new terminologies here like np and nu. So the first part is related with the system, let's say, behavior in future, and this is the behavior of inputs in future. And this np is the prediction horizon, and this nu here is the control horizon. So as you can see, they in this type of formulation they are not identical, but for the sake of simplicity we can take np is equal to nu, and this is, let's say, this is equal to n, which is a number. And of course in this case we can write a unified, let me say, representation, because when these sums, order of sums, are equal to each other, we can take this inside. And yeah, this is more or less what is done in the quadratic way of setting cost functions. So since they are some quadratic equations, we can represent it in this way. So basically there are two options here how we can form a cost function. One is the linear cost function that includes a linear equation, and the other one is a quadratic equation, which is more or less shown like that here. So quadratic way of formulation of cost function creates several benefits to us. I'm going to mention it briefly in the next minutes about it, but first of all, let's take this as an initial starting point and create a more generalized version out of it. So, and this can be written as something like that. Let's say minimize based on UK from k is equal to 0 to n minus 1. And this time, let's say, use the states of our system. Okay, so they are more or less, let's say, identical from the structural point of view, but in this one we are using states instead of the outputs. It's again quadratic because it includes the squares of each state and the input. So what we are doing here, so maybe I didn't mention it here. So what we don't have here in this one is weighting. So for example, if the error on the inputs are more important to me, then I can add a weighting factor here, and maybe before each of the specific input variables. so that I can make them more prioritized. Or if my output of your system is more important, then I can also weight that specific output or all output. So this is basically what we are doing here. And this weighting comes from Q and R. Q can be in different forms, but let's initially assume the very basic form of it, which is the diagonal. And the numbers on the diagonal basically becomes as the weights of each state. And it's the same for R. So the numbers on R becomes the weighting factors for the R input. And as you can see, the more value, the more weighting factor increases, the importance of that specific state or importance of that specific input increases to us, because when we have a state error or input, let's say error, this will be multiplied by that specific weight factor, and this at the end will increase the overall cost function, so which is not good. So because we are aiming to decrease this cost function, and we have also a terminal term here at the end. So when our QR and QN satisfy some certain criteria, this way of representation of cost function leads us to quadratic formulation, and this can be represented as something like that. Q should be a positive semi-definite matrix, and this can be written as like that, and R needs to be a positive definite matrix, and Qn should again be positive semi-definite matrix. Okay, so we have mentioned about some terms here. So quadratic form, positive semi-definiteness, and constraints comes in the, let's say, linear form for now. But what do they bring to us? So let's assume a very basic or formulation of a linear MPC, and let's again use this one, minimize this one, subject to a discrete time system, a linear one, and we have some state constraints here, a lower one and upper one. Also the same for the input variables. Let's say this is also equal. I'm sorry, this should be x and this should be u, and we have some initial conditions at the very beginning of our optimization. Okay, this basically formulates a linear MPC problem. So if these matrices satisfies these positivity conditions here, then we are ending in a quadratic problem. And what this quadratic problem creates us is that, so these conditions are here. If we have, let me say, equality or inequality conditions for x, this can be represented of let's say, mx is less than or n. So this is a vector, this is a matrix, this is a vector. So this means that our x variables lies between some boundaries, and these basically are some lines in our working space. And this quadratic formulation are basically some circles again in the same space. And from the geometrical point of view, this will end up something like that. Okay, this is not very well driven. So the curves that I'm driving here is basically the representation of this quadratic notation. So 1 over 2x times q x plus c times c equal to constant. So based on the values of x, so these circles or curves may expand. So for example, when they are all equal to 0, we are right at the center. In this quadratic formulation, we have some curves like that. In addition to this, we have some constraints like that, right? And all these constraints are basically some lines. And they may end up in a structure something like that. Of course, it depends on your constraints. And voila, here we have an interesting point, which is this one, because we also have a corresponding point for this one in the quadratic formulation. And this comes due to the shape of the quadratic problem formulation. And this point here indicates an optimal point for us. So we could do it only if we have the quadratic problem formulation, because otherwise these curves will have some different shapes and you need to make an extensive analysis on top of that, so deriving the solution may not be easy at all times. So this is a kind of benefit that comes from quadratic formulation of MPCs. One last thing that I would like to mention at this point, the formulation of linear MPC. Here we have the initial states x0, right? And this is basically creating a link between my current state and the next states of the system. So what I'm trying to say is that, so at the current specific time, I consider the initial values of my system, which is given something like that. And then I'm executing this optimal control problem and finding a control law ut, let's say. And then in the next run, let's say now the t is equal to 1, not 0. I have new x values here. So I need to use this new x values as initial values for me, and then execute the problem again, solve it, find new u values, and apply the first one out of it. So this basically creates a link between the system output and my problem formulation here. And this is quite important. So one last thing I would like to mention here at this point is that, so maybe you ask the question yourself that we don't have any reference value here like we did it here. So when we don't have any reference specifically indicated in the problem formulation, this means that I want my states to go 0, or I want my input variable to go to 0, which is less energy consuming point most of the time. But of course, this is not always the case. So if you have a different type of reference trajectory that your system wants to follow, of course, you can always integrate it to your problem formulation, and you can modify the structure of the cost function a bit. It's because of that, in the next minute, I'm going to briefly mention about the possible types of trajectories that you can use in your cost function representation. The last thing that I would like to mention about the constraint is that what kind of constraints type you could use in your formulation. And so I have sketched some of them here. For example, the first one is the constant set point. So you have a certain value that your system to be in there forever in this case. And so in this case, for example, the values here should be punished. So like this one, like here. So as you can see. So this is also briefly what I have mentioned in the previous slides. But of course, this is not the, even though it's some of the main options that you can use, it's not the only one. For example, here we have an operation band. So this means that I have y max allowed, y min allowed, and I want my system to lie somehow in between these boundaries. And in this case, this part should be, let's say, punished, and this part. For example, since it's inside the given operation band, so it's quite fine here, but for example, this is not fine. Another thing that, so maybe you have a unique profile of input or reference, and this could also be named as a trajectory that you want your system to follow, which is represented by a dashed line here. And when you have such a actual response, then this part should be somehow taken into consideration and, let's say, included in your cost function. So this becomes as the error signal for you. And the last thing is it's similar to operation band, but we have a, let's say, increasing exponential and logarithmic term here. So it's not a constant band, but it's converging into a certain operation band. In this case, as you can see, it's the band is quite big at the very beginning, and then it's decreasing and converging to a certain band. So in this case, for example, this one here is not okay. This one here as well. So these are the main options that you can use in your cost function representation for the MPC problem. Okay, and now we are going to jump into the constraints. The last thing that I would like to mention at this specific part of our lecture is the constraints. And of course, there are different type of constraints within the formulation of MPC, and they can be named as hard and soft constraints. So what is a hard constraint? For example, let's assume that you have an input signal to your system, and this supplies a kind of voltage signal or ampere signal to you. If it has an upper bound due to its internal structure or so, it's not possible for you to exceed this maximum value. For example, if it's 2 ampere, then the maximum value that you can supply to your system is 2 ampere. So this is a kind of hard constraint. But on the other hand, due to the flexibility of the MPC, there could also be some soft constraints. For example, if you have constraints for your internal system states, this may be sometimes softened. So this means that, for example, if you set a maximum bound for your internal state, you can still give flexibility for your system to go beyond this initially proposed constraints. But of course, in this case, you need to modify your original problem formulation, which I'm going to mention it in the next minute. Okay, so let's say hard constraints. And these are mostly related with your input variables, and they can be represented as, let's say, I have a lower value for my ETH input, and I want this to be within a band that also has a upper value. So this is a kind of constraint for your input. Of course, you may also want to restrict how fast or how slow your input signal is changing. For example, you can also put some constraints to the variation of your input signals, so that the UI is less than or equal to that UI upper limit. So this means that, for example, if you have a pump and you don't want your pump to make some reactions in an aggressive manner, you can also set these kind of constraints on your system. On the other hand, we have also soft constraints. And in principle, they can be violated. For example, let's say that you have defined something like that. You want your system yield to be in between something like that. Okay? If your yield is less than 0.75, it's not okay for you as it is. But you can still make some modifications and accept the yield values less than this value. So in order to do that, we need a select variable and then slightly move this inequality constraint. Slightly modify this inequality constraint. In this case, so this can be named as the constraint softening. Constraint softening. And for example, I have such an inequality constraint. And if I add an select variable, which is epsilon, this could also be represented as something like that. Cx plus epsilon is equal to d. So what we have here, if is epsilon here is equal to 0, then I have Cx is equal to d. If it's a greater value than 0, then I have Cx is less than d here. And this could also be written as like that. So what we have did here is we have relaxed the condition a bit. So when you compare those two, now we have an additional epsilon term. If epsilon is equal to 0, then we have our initial original constraint. But if it's bigger, then this means that we are creating a relaxation here. As I said, soft constraints can be softened. So, and I would like to explain this over an example case. Let's assume that we have such an inequality constraint. So this means that Cx should be at most equal to d, or in most cases, let's say less than d. Okay, so how can we soften this constraint if possible? So of course, we need an additional term, which additional variable. Let's say this can be named as a select variable, and this one can be represented as something like that, d plus epsilon. Okay, so and this epsilon should be either equal to 0 or greater than 0. When we have this epsilon equal to 0, then we are ending up with the original constraint here. But if this is greater than 0, then this means that we are relaxing the original constraint. Okay? So this is, in some certain cases, could be quite useful, but we should be careful when we are using such a thing, because so now we have an additional variable, and if my system goes beyond that limits, this means that when epsilon becomes a value greater than 0, then I should also inform my problem formulation that something is not 100% that I have initially planned. How this could be done? So I can go back to my cost function representation and add an additional term that's based on this epsilon value. And it could be something like that. Let's say minimize again based on uk and epsilon k. This time, so these parts are the same with the previous notation, xk q xk plus uk are uk. Okay, now this comes. Okay, and of course I need to have a terminal constraint like again. So what we have modified, so this part only. As you can see, when epsilon is equal to 0, then this part goes to 0 and I have nothing changed. So this is completely the same with the previous one. But if I need to, let's say, increase the value of epsilon in order this constraint to be satisfied as this in the relaxed formulation, then this new extra values added some extra values to my cost function, which says that, okay, this is not very good maybe. So in this way, you can set a relation between the constraints and cost function. And this, let's say, external time term can be written as equal concern for relaxation. In short, ECR. Okay, so this concludes this specific part of our lecture. In the next one, I'm going to summarize the tuning parameters for MPC and make a conclusion.